Question 3, so we have this spontaneity or feasibility of a chemical reactions. We're talking about the Gibbs free energy change, which is related to enthalpy as well as entropy. This is for the system. We are looking at for the system, which is the reaction itself. All right. So we have to state and also explain whether the following processes will lead to increase or decrease in entropy. So the entropy change is going to be the entropy, well, the sum of the entropy of product minus the sum of the entropy of reactants. So what do we have here? Magnesium plus hydrochloric acid. If you think about it, magnesium plus HCl, you will get MgCl2 and you will get H2 gas. This is a classic reactive metal with acid, with a strong acid there. Mg2 plus being a group 2 metal, Cl minus group 17 anion. So that reaction produces a gas. So that is a solid. This is aqueous. This is also aqueous, and this is a gas. So you go from no gas to producing a gas. So the entropy change will be positive. So the magnesium plus 2HCl reaction produces H2 gas. Entropy of a gas is so much bigger than entropy of a liquid, so much bigger than entropy of a solid, and this is actually exactly as stated in the syllabus as one of the things that governs entropy change. The next one is to do with solid potassium chloride dissolving in water. So what we have is KCl solid. You dissolve in a large amount of water, then you get K plus aqueous plus Cl minus aqueous. So all potassium salts are soluble in water. So what actually happened? The solid, in the solid state, the ions are held in a fixed lattice, the giant ionic lattice. The ions are not free to move. They are ordered, regularly arranged in that ionic lattice. As you know about a solid state structure, they only vibrate about fixed positions. In an aqueous solutions, the water is surrounding the cations and surrounding the anions. The ions are free to move. That's why aqueous ionic compound can conduct electricity, because the ions are free to move. So the entropy change again will be positive. Hang on, positive. Entropy change is positive, so we get an increase in entropy. So the question really is asking increase or decrease in entropy. So really I shouldn't really use positive, I should say increase in entropy. Okay, so I say it's positive, meaning to say I go from lesser entropy to greater entropy. Entropy is a measure of randomness in the system. Okay, these are definition of entropy. So the more disorder I have, the greater the disorder, the greater is the entropy. If I have greater entropy compared to what I started with, that means I will have increase in entropy. Okay, so KCl solid, potassium chloride solid, has very little randomness, very little disorder due to its position in a fixed lattice, due to its position, has very little disorder. I think that should be enough because I'm running out of space, but it's actually due to the solid state. Okay, the solid state where the ions are in fixed position, whereas K plus aqueous and Cl minus aqueous are free to move. They are mobile, they are mixed around. Okay, so much more disorder, much more randomness in terms of their motion. Okay, the next one is to do with H2O gas. H2O gas turning into H2O liquid. The entropy of a liquid, or the entropy of a gas, I guess. The entropy of a gas, so this is a change of state, is a lot bigger than entropy of a liquid. So you are going from something with high order of randomness to a low level of randomness. So you will have a decrease in entropy. You will have a negative entropy change, just like what we said earlier. When you produce a gas, because of this, then you have increase in entropy because you go from no gas to gas. Here you go from having a gas to no gas, you decrease in entropy. So next one, they've given us enthalpy change, and this thing is Gibbs free energy in kilojoule per mole. This thing is kilojoule per mole. These are entropy values for each of the substance, and these are given in joule per mole per Kelvin. The first thing you do really is work out the entropy change of the system, which is for the reaction. So it's the sum of the entropy of the products on the right hand side, the sum of the entropy of the reactants on the left hand side. So what you get then is you have 1 time plus 26.9, because you have 1 mole of it, times this plus 1 times plus 214. So the use of bracket, I cannot overstate its importance, okay, because a lot of students will make a mistake here and there if they are careless. And if you try to rush calculations, there's usually very bad decisions. So use bracket very carefully. And then minus, I'm actually running out of space, to be honest. Having said that, I suppose you can really make full use of space, and I was hoping for a 3-mark question they would have been more generous with the use of space there. So it seems like they give us very little space for 3-mark, and that is ridiculous actually. Okay, anyway, that question is not complete. I still need to complete it off. So delta G, in fact they've given you delta G equal to delta H minus T times delta S. That is actually a definition that you have to know as part of your delta G definition in the syllabus. So delta G would have to be in kilojoule per mole. So later on I need to convert this to kilojoule per mole by dividing by 1000. This is a plus. Your calculator will not show you the plus. You need to be careful. Sign value units for every single thing, including enthalpy, entropy, and Gibbs. Alright, this is physical chemistry. So plus 117. This is supposed to be in kilojoule per mole. This is in kilojoule per mole. The temperature is at 29 Kelvin, so it's 29 Kelvin. I am going to multiply that by plus 175.2. Plus 175.2 is from here, but that is in joule per mole per Kelvin, so divided by 1000, and that will convert this into kilojoule per mole per Kelvin times Kelvin. It will give you kilojoule per mole, that you can then sum in the kilojoule per mole to give you this thing in kilojoule per mole. So plus 117 minus 298 over 1000 times plus 175.2. My calculator show me 64.7904. My calculator does not show me a plus. That is up to you to remember, okay, that everything you do is to do with sign, value, and unit, and this is in kilojoule per mole. They want the answer to 3 significant figure, 1, 2, 3. So look at the fourth one. This is bigger than 5, so I add 1 there, plus 64.8. This is 2, 3 significant figure, sign, value, units, and they want a 3 significant figure. Okay, now explain with reference to delta G why this reaction become more feasible at higher temperatures. Okay, so what happened when temperature increase? All right, so we have to not only look at delta G. In fact, delta G is computed as a result of delta H and delta S. So I really need to look at the whole picture by comparing the sign of delta H and delta S. So the delta H is greater than 0, so it's endothermic. Doesn't matter it's endothermic or exo, but the sign itself is greater than 0. That's important. But delta S is also greater than 0. Delta S was greater than 0. So when temperature increases, temperature in Kelvin is always positive, right? The lowest is 0 Kelvin, and it will go higher and higher because there's no negative Kelvin. So when temperature increase, T times delta S becomes more positive. And if T times delta S become more positive, then delta G will become more negative because this is minus T times delta S. So delta G becomes more negative. So we compare one thing leading to another. This is positive, so T times delta S become more positive, minus T times delta S become more negative. Therefore, delta G become more negative. And when delta G becomes more negative, therefore, more feasible at higher temperature. So delta G lesser than 0 means the reaction is spontaneous. The lesser it is, well, the more negative the delta G is, the more feasible, the more spontaneous is the reaction. Next up, they want you to use the data in the table to describe the trend in solubility, only for 1 mark, yeah? So looking at the table, so KSP for MCO3, group 2 carbonates, you see the -5, -9, and -10, they get smaller. They get smaller down group 2, okay, meaning the solubility decreases, okay? Their solubility decreases, or decrease actually, down the group. Okay, so KSP is to do with this idea where you dissociate into the aqueous ions. Basically, it's solubilizing the salt. Okay, if you dissolve more, then you favor more to the right hand side, then your KSP value is getting bigger and bigger. Okay, when it's at 1, it's at equilibrium. When it's much bigger than 1, it favor more to the right. When it's lesser than 1, it favor more to the left. All right. In fact, they want you to show the equilibrium. To show the solubility product, you got to show stat symbol. See what I've done there? Okay, the stat symbol is part of the definition, yeah? They want you to show for MgCO3. So it's MgCO3 is solid, giving the group 2 cation, giving the CO3 2 minus anion, all right? What is observed when you have a few cm³ of concentrated Na2CO3? So all sodium salts are soluble in water. Okay, you learned that in O level or GCSE. In fact, you will have seen aqueous sodium carbonate before. You add it to a saturated solution. You see, solution. Saturated means it's the maximum amount of this solid that can dissolve in water. So it's colorless, it's clear, it's aqueous solution. Okay. So what happened is Na2CO3 is completely soluble in solution or in water. Okay, in fact you have aqueous. All right, so you have Na2CO3 going to Na plus, 2 of them, plus CO3 2 minus aqueous. Okay, so as it is added, the concentration of CO3 2 minus in a square bracket increases. Therefore, for the KSP equilibrium of MgCO3, when you have this and this together, that means in the solution mixture you have a lot more of this compared to that. But when this concentration increase, what would this equilibrium do? Okay, this equilibrium will try to decrease the concentration of CO3 2 minus. The equilibrium will try to decrease the concentration of CO3 2 minus. Therefore, it will shift to the left. We are talking about the KSP equilibrium, yeah, because that is equilibrium, there's no equilibrium. The equilibrium here will shift to the left to try and decrease the concentration of this due to the addition of sodium carbonate, which increased the concentration of CO3 2 minus in the solution mixture. If you shift to the left, that means lesser of this is soluble, therefore you will precipitate it out. Previously, you have a saturated solution. Now, therefore, MgCO3 will precipitate out, or you can say MgCO3 solid will form. All right. So this is what they call the common ion effect. So just simply stating the effect is not going to help you. It has to be in terms of Le Chatelier principle and what happened in the context of adding the CO3 2 minus. All right. So because our temperature doesn't change, still remain at room temperature, our KSP will not change. All right. But they want the solubility. Okay, they want in gram per dm³. So this is a bit unusual. They want it in mass concentration. Okay. What can I do? These are in mole square dm minus 6 because there's solubility product. So perhaps I can write an equation. No, actually I already gotten the equation. So here you can tell if if I have x mole of this that dissociates in solution, therefore I'll get x mole here and x mole there because it's 1 mole is to 1 mole. Alright, 1 mole of this dissociate to give you 1 mole of that and 1 mole of that. X mole of this dissociate in solution to give you x mole of it and x mole of it. All of this is in the same volume, so these are mole, therefore you can convert it to mole per dm cube. It's going to be the same as well, yeah, meaning to say they are over the same volume. So if this is the concentration, okay, so now I'm talking about concentration, no longer mole of this MgCO3 that dissolve in solution. These are going to be the concentration of Mg2 plus and CO3 2 minus in solution. So Ksp, the one for the magnesium carbonate, so I'm writing the expression for it. Both of them, the power is raised to 1 because the balance equation show you 1 and 1. So I got use the value 1.0 times 10 to the minus 5. That is 1.0 times 10 to the minus 5. Actually, I'll move the value down there. So that is equal to x times x. So that is x squared. Alright. Because I want the solubility of MgCO3, which is that. Alright. So I need to find x. So therefore x is the square root of that. Remember that will be in mole per dm cube. So x is 3.1623 times 10 to the minus 3 mole per dm cube, and they want it in gram per dm cube. So that is not the end of it. So x is the concentration of MgCO3 in mole per dm cube. Alright, so mole, well, I hope you know this from your O level really. Mole is equal to mass over mR. Okay, divide by dm cube both sides, you will get mole per dm cube, you will get gram per dm cube, you will get gram per mole. So that's the relationship between molar concentration and mass concentration and molar mass. So 3.1623 times 10 to the minus 3 is equal to your concentration in gram per dm cube divided by your MR. So this one you get from the data booklet. So 24.1 plus 12.0 plus 16.0 times 3. I think I must have keyed in the wrong value. 84.1 gram per mole. So therefore I can get the concentration in gram per dm cube by multiplying the concentration in mole per dm cube by the molar mass, which gave me 0.2659. All these data were given to two significant figures. I have used them in my calculation. I should round it up to two significant figure. That is called appropriate number or significant figure based on the data given in the question. Alright, so that's it in this question. So moving on. Part B, as I mentioned, is one of the common essay. They want you to describe and explain. So typically we know the train from AS already. So from AS, you know that we talk about thermal stability of the group 2 carbonate. They become more stable to heat down group 2, and the result, well, the explanation for it is down group 2. In fact, we don't use the Roman numeral in A level, we use the Arabic numeral because we go from the numerical value 1 to 18, where you have 3 to 12 in the across the transition metal period. Okay, so down group 2, there are more field electron shells, so for obvious reason, then the ionic radius, which is radius of the ion, increases. And for the same charge are +2 for all group 2 cations. Therefore, what am I talking about? Charge density. Yes, charge density of the M2 plus, meaning the cation, decreases because same charge but size increases. So what happened? Should probably don't put 2 there. Maybe I'll put 2 there. Then I'll just change this to A and B. Well, I don't want to put 1 and 2 because that will mean that it implies that this is explaining 2, but it's not. I'm going to explain first and I'll describe the trend a little bit. So charge density at M2 plus decreases. Therefore, M2 plus polarizes the anion, which in this case is CO32 minus, because we read the question. When it's nitrate, we don't write carbonate. When it's carbonate, we don't write nitrate. So it polarizes the anion less, because you have lesser charge density, so you polarize the anion lesser. Therefore, you weaken the CO covalent bond lesser, and therefore more difficult to break, since we need to break the CO covalent bond in order to give off CO2 and the group 2 metal oxide. So if it is more difficult to break the covalent bond, therefore this should be point number 4 already, hence more stable to heat or more thermally stable. Down group 2, more thermally stable MCO3, which is M2 plus CO32 minus, down group 2.